Welcome, ladies and gentlemen. Let's go ahead and review our strategy for linear programming, right? When we use linear programming to find the optimal solution while working within given constraints. And so first thing we want to do is identify the variables. We've got to let x equal the number of bags of Red Hots and y equal the number of juice box, or let x equal the number of IT05 video games produced and y equal the number of IT08 video games produced. So our first step is to identify the variables. Next, we're going to write the blank as a system of blank. What? Well, we're going to write the blanks as a system of blanks. So what do we have for that? Jared? Absolutely. Thank you. We're going to write the constraints as a system of inequalities. Absolutely. Thank you. Then we're going to write in blank blank for the quantity to be optimized. So let's write in blank blank for the quantity to be optimized. What's that going to be? Doc?
Is going to be write an objective function.
Absolutely. An objective function or objective equation? Absolutely. Thank you. Step 3, we'll graph and shade the blank blank and include the coordinates of the blanks. What? Graph and shade the blank blank and include the coordinates of the blank. Let's do the first blank blank. Graph the shade of the, Megan? Feasible region. Nice job. So we're going to graph and shade the feasible region. Thank you. And include the coordinates of the blanks. And so what are we finding? The coordinates of the blanks. Ian?
Vertices.
The vertices, right? The corners of my feasible region. The vertices of that polygon. Good. Thank you. Blank each vertex in the objective function. Hey, easy. Careful how you fill in that blank. Blank each vertex in the objective function. Joe? Test it. Absolutely. We're going to test each of those vertices, those critical points in my objective function, scan those results, and so we can do step 5. We're going to state our decision about the best choice for the situation. So lastly, we'll state our decision about the best choice for the situation. Raise your hand if you had responses that match these, right? You could share your results or make your decision. This would be fine too. Awesome work, you guys. Way to go. What questions do you have about our linear programming strategy? Okay. So what we're going to do first is check our dance and skate linear programming worksheet from last time. I'm going to go ahead and pause the recording while we do that. Okay, ladies and gentlemen, thanks for your help grading your assignment. Today I'm super excited about, again, we're going to switch gears from working within the video game constraints to an astronaut problem, where you're charged with the task of determining the best combination of nutrition to bring along with you up into outer space. This is a great activity. I want you to know that this activity is a little bit trickier than last time. So what we're trying to do is slowly raise the level of complexity to make sure you're able to solve more difficult problems using the same linear programming strategy that we outlined for both. So first, let's recap our video game problem. We saw that depending upon the number of 05 models and 08 models that your team decided to produce, you'd either produce a profit or not match all your constraints, and so you get not feasible. So if we went ahead and graphed the constraints on the XY coordinate plane and labeled the feasible region, we could find the corners, right? The corners of my feasible region, either through inspection, in the case of those intercepts, or by solving a system. And that's what you're going to have to do today. And so in order to find this intersection point, right, we have to go off to the side and make our own little system of equations. The intersection of those two slant lines would be the solution to the system that included the equations of those boundary lines, those slant lines. And so if I wanted to find that intersection point, I would go ahead and set up a little system on the side that had just those two equations in it. The 0.2x plus the 0.4y equals 160, and the x plus y equals 500. The reason I'm doing that is because today, right, you're going to have to go ahead and set up a system to find those intersection points. They're not going to be quite as nice as like the 200, 300, and the 300, 200 that came out of your activity. What would I do if I wanted to figure out that intersection point, right? What would the equations in my system be if I wanted to figure out that intersection point? Go ahead and decide and then tell the class when I call on you. If I wanted to find that intersection point, what would the equations in my system be? Maya?
I don't know.
Well, which two boundary line equations intersect, right, to make that star?
X plus y and 0.6 x plus 0.0.
Absolutely right. And so we'll go ahead and scan, right? We'll scan. That's why it's just as important. Almost made it. Not quite. We want PDFable, striving for PDFable all day, every day. Thank you, Maya. In order to figure out the blue intersection point, I'm going to take the two slant line equations that intersect to make that intersection point and write a little system on my side margin and solve that in order to get the coordinates of that. And so the reason we're taking a look at this video game problem, even though you guys have already solved it successfully, is because sometimes the intersection point isn't just so nice on the grid, right? An integer point on the grid. You'll have to solve for it algebraically, and that's what you're going to have to do today. What kind of tools could you use to solve these systems? Well, what method might you use to solve this green system? Everybody think. What method might you use to solve this green system? Aaron?
Substitution.
Certainly, we could solve this system by substitution if we rearrange the second equation to solve for y, or solve for x, and then substitute it back into the top equation. Everybody see the x or y, respectively, and then solve. What about the blue system? Right? What method might you use to solve this blue system? Hannah? You could use substitution as well. You could add or subtract to get the x or the y alone in that first equation and then substitute back in the other one. You could also use elimination because the x's and y's are lined up. If multiplying through by a negative 0.2, we could create exact opposites in the x's in that first equation, or in the second, by multiplying through by a negative 0.3 on the top equation, we can create exact opposites in the y's, or what have you. And so you've got lots of tools at your disposal. One method that might be easiest today is to solve each of these for y and enter them in your graphing calculator in the y equals menu. Graph on the same window and do second calculate intersect. And that's why we included that towards the end of activity 1. The second calculate intersect button is going to be an important tool if you work with more complicated equations that don't work out so nicely. Okay? So that's where we're headed today. All right, after testing those boundary points, the vertices, the critical points of your feasible region, we saw that the winning profit, $32,500, resulted when 205 models were created and 308 models were created. And so we know that my variables, we let x be the 05s and y be the 08s. We had constraints within which to work. We had an objective function. We know that the feasible region was where all the conditions were satisfied. The corners of the feasible region are the critical points, and we tested those in our objective function before stating our findings. Today we're going to switch gears and look at a different context. You're going to be put in the role of an astronaut planning team where you're going to determine the optimal combination of food bars and energy drinks so that the nutritional requirements are met as you go into space. And so we're going to do number 1 together. Then we're going to take a look at number 2 to 6 and summarize the math with your groups and your cooperative learning groups. We've got stamped eligible items that include number 4. 5 is the graph, and so after you guys have your graph correct, that's a stamped eligible item. 6B, and then the summary number 2. And so the summary number 2 then is your 4th stamped eligible item. For number 5, you want to find the vertices of your feasible region using the calculator. That is the second calc intersect, or the matrix, right? The matrix equation. So second calculate intersect would allow you to do that, or you could set up matrices in your graphing calculator. Some people like to use the matrix editing menu in order to solve their systems, and that's totally fine as well. When you're done with your last stamp, summary number 2, then you begin working on assignment number 9. You can do that together. Again, just 2 linear programming problems again for homework. There's no book work, and that's your worksheet. You want to make sure you're done with activity 2 if you don't finish it in class so that you can get all 4 stamps for activity 2. Questions about what the day is going to look like? Okay, then let's go ahead and take a look at our linear programming activity 2. And I'm going to pause the recording now